Alright guys, welcome back. In this video here, we're gonna discuss the introduction of the new concept that we're gonna use. Well, the most important concept in addition to limit is derivative, and this is the concept that we use throughout the entire semester. So we need the concept limit to be used as part of the definition of the derivative. So we're gonna discuss what it is in this lesson. And then we're going to go through how to find the derivative of certain functions. And then the next chapter, actually at the end of this chapter, we'll learn this shortcut to find the derivative as well. So let's start by just consider this example here, kind of briefly introduce what the lesson is all about here. So suppose you have a car, travels 110 miles in 2 hours. The question is, how fast does the car travel, right? So not much information given there. You know that the total distance given, right? And you know that the duration of the trip, which is 2 hours, and it's asking how fast does the car travel. So normally, a problem like this here, we use the formula distance equal to rate times time, right? So you have distance is 110, and then you have the time is 2, and then you have to find the rate, which is the speed, right? So you get rate is, or the speed is 110 divided by 2. So that's 55 miles per hour. So, but here's the thing, right? We don't know, well, let's just put it this way. This 55 miles per hour is not really how fast the car travel for the entire 2 hours. The car might be travel 80 miles per hour at some point during the 2 hours period, or 45 or 50 or 47.5 miles per hour. We don't know. So this speed here, this here represent the average speed for the duration of 2 hours, right? So if I was to represent this problem here, this example through a graph, okay, suppose we have this graph, and this graph describes the speed of the car. Let's say this is 55 miles per hour, right? Here's 1, here's 2, so this is hours. So the car doesn't really go straight. Oh, sorry. The car doesn't really have a constant speed for 2 hours, okay? That's not realistic, okay? The car might be doing this here, right? It might be start low at 0, and it's going to jump up to past 55, and then maybe go down and hit the traffic, go back up again, and maybe it does that, right? So we don't really know the actual speed of the car at any moment between the 0 hours to the 2 hours. But the 55 miles per hour is just the average speed. And usually we tell people like this, right? But imagine you driving to Tahoe and doing your trip to Tahoe. It's about 2 hours. Imagine as you're driving and you're trying to figure out how fast you're going. And so at that moment, you look at your speedometer, and at that moment, it will tell you how fast you're going at exact moment. Okay, so that speed there is not the average speed. That speed there is the moment speed, or the instantaneous speed. So that's where the derivative is going to come in. Okay, so what I mean by that is, let's say during this 2 hour trip here, you look at your speedometer, and then that might measure at 45 or something, right? Or maybe here is different, or maybe there is different, maybe they're different, right? So at this moment here, that we call that right there is the instantaneous speed. Okay, and so the derivative is going to measure that. Okay, so that's where we're heading here. So so let's talk about the formula to calculate the average speed first, because we need that formula to introduce the instantaneous speed, or this average speed here. So the average speed, another word for average speed, just the average rate of change. Okay, and then this instantaneous this instantaneous speed is just instantaneous rate of change, right? There's two rate of change. One is the average, is what we've mostly known by, and the other one is instantaneous rate of change. This happens at any moment in time, and while you're driving a car, you look at your speedometer and tell exactly how fast you're going. So I'm going to introduce the formula for the average rate of change, and this formula may look familiar because we use this all the time in algebra. Okay, so definition, so we said definition, okay, average rate of change. So the definition say that for a function y equal to f of x, okay, we define the average rate of change from a starting value x equal to a to an ending value a plus h, is the following formula. Okay, it is equal to the output at the end of the output value of the endpoint minus the output for the beginning point, divided by their difference of the inputs, the two position. So notice that in the denominator, if you look at a plus h minus a, the a is going to subtract the a out, so that's going to be 0, so that just leaves us h in the denominator. Okay, so, and then this is only defined when h is not 0. Which makes sense because h is the distance, the displacement from the position a to a plus h. So the distance h can't be equal to 0. So if you look at this here, this formula here, right? Recall this formula. If you have 2 points x1, y1, and then x2, y2, all right, and you ask to, let's say here's the 2 points here and there, and you ask to calculate the slope between these 2 points there, right? So slope, right? So this is from algebra. We say, okay, well, the slope formula is just the change in y position over the change in x position. So if you look at this formula of the average rate of change, it's simply the same formula. It's just on the numerator is a change in y, and in denominator change in x. It's just the way we choose to label these position x1 and x2 as a and a plus h, so that way we get a different slightly formula here. Okay, but the average rate of change is just another look at, you know, slope formula. Okay, if you remember from algebra. Okay, so let's apply this formula and do an example, so that way we can get a quick refresh how to use this formula here. Okay, so in an application concept, you have a revenue dollars from sale of X plastic planter. Okay, planter box is given by this formula. Okay, so r of x equal to 20x minus 0.02 x squared is the revenue function. Describe the revenue in dollars from selling X number of plastic planter box, right? A is asking for what is the change in revenue if the production is changed from 600 to 800 planters. So this is saying, okay, if we produce 600 planters currently and then we go up to buy 200 planter box, okay, what will be the change in revenue? Okay, so let's go ahead and do that. All right, so A, let me use different A. All right, so the change in revenue from X equal to 600 to X equal to 800, that's just saying, okay, evaluate the total revenue at 800, subtract the total revenue at 600, and that'll give us a change in revenue. Okay, so we plug this number into the revenue formula. So that's the R of 800, okay, minus R of 600, so it's 20 times 600 minus 0.02. This should be a square there, and then 600 square. All right, plug this into your calculator, and if you do the math right, you should get the answer to be a negative $1,600. So the change revenue is the revenue went down as production increased, which makes sense. You got to keep up with the demand, otherwise you're not going to make any money. Part B is asking for what is the average rate of change in revenue for this change in production. So this is saying that, okay, well, if the company produced from 600 planter box to 800 planter box, overall, what would be the average change in revenue for this 200 units of increments here? Okay. So we said, all right, so B. Okay, so the average rate of change, from x equal to 600 to x equal to 800. And that's just taking the revenue, the change in revenue, okay, minus the change in production. In this case, it's going to be 200 difference in term production. We know that that is negative 1600 on the top. So that would give us negative $8. So I'm going to go ahead and interpret this is negative $8. Okay, so the way we interpret this is that, oh my God. All right, so let's go ahead and do this again. Negative $8. The way we interpret this as, we're saying that the average rate of change is decreased by $8 per planter box. Okay, so that's what we're saying there. So if we look at this geometrically, the graph could be, let's say this is x, this is r of x, and here's 600, and here's 800, right? So let's say at 600 is somewhere this value, 800 is maybe it's gonna be decrease, so it's up here and then decrease there. So we're saying that, you know, the average rate change has a negative slope, so what we calculate there, we calculate the slope, the average rate change. That's just by, you know, that's just by this negative here, this m here is just negative 8 per planter box. That's what we just did. Okay. So the average rate of change formula is just like computing the slope for 2 points or just a linear line there. So now let's introduce the formula for the instantaneous rate of change. And this is where we need to use the concept of limit, which we introduced in 2.1. Okay. And I'm going to go ahead and do that in the next video.